Ну хорошо. Давайте. Okay, so let me start by. I'll start by recalling what we did last time. So. So we studied ramification. And so the setup is the following. So we have some discrete valuation ring. We have maximal ideal. We have the residue field. And we have the fraction field. And we have finite separable extension. And this time I will even assume that it's a Galois extension. Extension, finite. And say we are interested in the Galois group of L over K, and let it be G. And we have integral closure. So this is in K, this is in L. Okay. Then, we know that B has finitely many maximal ideals. Maximal ideals. B. And we have some invariance of this extension. So we have the residue fields of Mi, and so these are finite extensions of K, and all the degrees are equal, and we call this number F, and they're equal because the Galois group acts transitively on this set of maximal ideals. And also, we have ramification indices. So one way to define it is to consider the ideal of B generated by the maximal ideal in A. And then you can write it, because this is a Dedekind domain, you can write it as M1 E times M2 E. And again, all the exponents are the same. And so we have these two integers, and F times E times the number of ideals is equal to the degree. Okay, and so have some numerical invariance. And then we started the Galois group. First of all, we have decomposition group. Decomposition groups. This is a stabilizer of Mi in G. So stabilizer in G. Okay. Of Mi. And then so this decomposition group, well, it acts on B, and it preserves the maximal ideal, so it acts on the residue field. And it defines a homomorphism from this decomposition group to the homomorphism group of the residue field extensions, and we showed that this homomorphism is surjective. And the kernel is called the inertia group. Okay? Now, so it follows from this short exact sequence. Well, we can compute the order of the inertia group. So the order. So what is it? I claim that this is E. Times the degree of, it's equal to E if this field were separable, but otherwise it's inseparable degree. So K mi separable, right? So why that? Okay. So let's see. So we know that the So this follows immediately from this formula and from this short exact sequence. So what is order of dmi? This is order of G divided by N. So this is F times E. Now, F is the degree of this extension over, the order of this group, right? So inertia group, the order of the inertia group is then equal to order of D divided by the order of this group. This is a normal extension, but it need not be separable. So it's divided by separable degree. And if you compare this, so if you use this formula, if you substitute it here, you'll get the result, right? F is the product of this number and this number. So good, and then we studied the inertia group. Maybe I'll write it here. So we defined a homomorphism from inertia group, we call it phi, to the group of roots of unity of eth roots of unity here. This is mi. Okay. So how we define this? Well, so I acts on B, it preserves the maximal ideal, and it acts trivially on the residue field. So, well, since it's, it preserves the maximal ideal, it acts on mi, modulo mi squared. It acts on this vector space, and it acts by k of mi linear transformations of this vector space, right? So why it's k mi linear? Just because I is in the kernel of this map. It acts trivially on the residue field. This is a vector space over this field. So this is a one-dimensional vector space over this field. So it's just k m I star. And this is our phi. So, and the image, because it's a homomorphism, the image must be a root of unity. The image is contained in the group of roots of unity. So now, so what is the order of this group? So what we, so the statement, first of all, that we proved last time is that, so proposition, what was kind of a key proposition, is that the kernel of phi, I will call it capital Pi, and this is called the wild inertia, is trivial if characteristic of the residue field is 0, and a P group if characteristic of K is P greater than 0. Okay? A corollary of this is that phi, well, so let's see. Okay, I'll state corollary. So let's write E as a product of E prime and some power of P. E prime is relatively prime to P, and P is the characteristic of K. So if characteristic is 0, then set E prime is equal to E. Then phi is surjective. Well, so you have inertia group, and it maps to roots of unity here. Well, so if this is a field of characteristic P, there are no roots of unity of order P. So this group is equal to this group, whatever it is. And so I claim that that this group is isomorphic to Z mod E I prime Z. So that is to say that there are this field, this residue field, contains all roots of unity of order E prime. Right? So there are this corollary, well, that's first claim, and the second claim is that this map is surjective. So there are two claims in corollary. First of all, the map is surjective, and that you have all roots of unity. You can expect. So why that? So the order of E is equal to E up to a power of P, right? So we have this formula, and this is a power of P, right? And the kernel of this map is a P group. Therefore, the image, well, this group has order relatively prime to P, right? Again, because there are no roots of unity of order P. So it means that the image proof image of Phi is equal to, its order is equal to E prime. Okay? Because it catches the prime to P part of E, of I. And this proves both statements. Mm-hmm. And the fact that this is cyclic is a general property of fields. Any finite subgroup of multiplicative groups. Good. So this has an interesting corollary. This proposition. Ну, вот этот гомоморфизм, он некоторую группу, у которой порядок взаимно прос P. Значит, порядок образа заведомо не делится на P. С другой стороны, ядро — это P-группа. Хорошо? И вот у нас еще есть такое. Значит, порядок всей этой группы, он равен, so this is equal to E prime times power of P. Okay? Good. So, corollary. Inertia group is solvable. Indeed, you have a normal subgroup, this wild inertia group, which is a P group, or 0. And every P group is solvable. And it's normal. And the quotient is abelian. Mm-hmm. So, corollary, Galois group of QP bar over QP is solved. That is to say, any finite extension, finite Galois extension of QP has solvable Galois group. Why is that? So you have you have QP. This is our K. This is finite extension, Galois group G. So A is ZP. This is complete. And we observe that if A is complete, then there is only one maximal ideal in the normalization, in the integral closure. It's a local ring, right? There was a simple argument. So N is 1. Therefore, the decomposition group, well, I will, so I have B in L. Decomposition group. So here I have maximal ideal, only one maximal ideal, and this is a name for this. Okay, so N is 1. The decomposition is the whole group, right? Because there is only one maximal ideal. And here I have the inertia group, and I already know that it's solvable. And the quotient is, well, it's Galois group of the residue field extension, K of M B over K. Well, in this case, it's FP. Right? So this group is solvable, and this group is abelian. It's a finite extension of a finite field. Very good. Yeah, so now so here is a definition. We will say that a Galois extension is thin if, one of the three equivalent conditions hold. So the order of the inertia group is not divisible by characteristic of the residue field. For example, if characteristic is 0, then every extension is stable. Observe that the Galois group acts on maximal ideals, on the set of maximal ideals transitively, and it follows that decompositions group are all conjugated. And also the inertia group are all conjugated. So it's enough to check this condition for one I. And this is equivalent to saying that the ramification index is not divisible by characteristic and characteristic of K, and the residue field extension, so K Mi, is separable. And the last condition is that phi I is an injection. Okay? So let's see why these are equivalent. So I know that the order of this group is, so let's see if I still have, yeah, right. So if I know that the order of this group is not divisible by p, then I know that E is not divisible by p, and this is 1, because it's a power of p, and vice versa. So, and why this is equivalent? Well, so phi I is a homomorphism to a group of whose order is relatively prime to p, right? This group, and kernel of phi I is a p group, so it follows. Good. So, yeah, I want to, so we have let's look at an example. So all this gets simplified when let's assume that A is complete. Well, we have all the setting that we had before. So A is a DVR, complete DVR. And I also assume that K is perfect. So we fix some finite Galois extension, finite Galois, and I want to describe for you explicitly the this group. So well, I cannot do everything, but I will describe for you kind of the finite Galois. Well, here is what I want to do. So we have again n is 1. So we have the composition group. I will not put index here because only one maximal ideal. It's the whole group G, as we already observed. And so I have G. I have the inertia group. And I have the kernel of this homomorphism, phi, which is called the wild inertia. So this is a subgroup here. And so P is, again, it's the kernel of phi. And so what we have is that I modulo P maps isomorphically using phi to roots of unity in the residue field extension. So we have a chain of normal subgroups in G. So it corresponds to intermediate extensions. So you have by Galois theories, you have K, you have L, and here you have the smallest subextension corresponds to largest group I. So this is it's called K non-ramified, and this is just invariance in L with respect to I. So, and we have K theme, which is LP. And I want to describe for you explicitly the structure of this extension by generators and relations. So it turns out that the Galois group of a fraction field of a complete discrete evaluation domain can be complicated due to, well, because this group, which is a P group, can be very complicated. But this group can be described explicitly, and the description is uniform almost in characteristic 0 and in characteristic P. Okay, so well, first of all, we know that this Galois group of non-ramified, unramified extension so extension is said to be unramified if the inertia group is trivial. So this is, so if you start with any extension, you can take maximal unramified subextension, and its Galois group maps isomorphically to Galois group of the residue field, which is K of MB over K. Okay, so this residue field is the same for this field and for L, because K is perfect, and therefore that field is also perfect. So you don't have, you already catch all the extension. So, well, how to construct unramified extensions of K? You can take any extension of this little k, so of the residue field, and you can, so it's separable, it's finite separable, so it's primitive, it's given by, by joining a root of polynomial with coefficients in k, and you just take the same polynomial, you leave the coefficients arbitrary. So you take a polynomial, monic polynomial with coefficients in this field that defines an extension, and you leave arbitrary the coefficients to get a monic polynomial with coefficients in A. So this polynomial will be reducible because it's reducible modulo maximal ideal, and it defines an étale. So if you, it defines an unramified extension of K. An étale cover of spec A. Okay, so now what I want to say, so proposition. So let's describe this extension explicitly. So I claim that K theme is obtained from unreamified extension by adding root of some element e prime root of A, where A is, well, let's say, has norm 1 in Kt, in K unreamified. So where A, so in particular, it belongs to the integral closure. It's an integral element, and it has norm 1. So what does it mean? So you have this field. You have ring of integers, the integral closure of A in this field. It's a discrete valuation domain. Therefore, you have the notion of discrete, well, the valuation. And, well, maybe, let's say, valuation. Valuation. Not to confuse. Well, so that's the assertion. Proof. Okay, so this is an exercise in Galois theory. So what do we know? So what do we know about this extension? So it's a Galois extension with a cyclic Galois group of order E prime. So first observe that by Hensel lemma, K unreamified has all E prime roots of unity of 1, right? Why that? Because the residue field has all roots of 1. And this polynomial, E x to the E x to the if power minus 1 is separable in the sense that it has no multiple roots modulo the maximal ideal, right? E prime is relatively prime to the characteristic. So, and I know that it splits completely in the quotient field, in the residue field, right? By this property. Therefore, it splits completely in splits in here. Now, so we are in the following situation. We have a Galois extension with cyclic Galois group and of order E prime, and we have all roots of unity of order E prime here. Then by Kummer theory, every extension, such extension, has this form for some A. How you construct A explicitly? So you look at the action of the Galois group, this group, which is I mod P. It acts here. And so you think of this as a vector space of dimension E prime over this field. And you have an operator, generator of this group. It's generated by one element, sigma, of order E prime. So you have a vector space, an operator of order E prime. So it's diagonalizable because you have all roots of unity of appropriate order. And you take its eigenvalue, eigenvector corresponding to an eigenvalue of, well, which is a primitive root of E of order E prime. That gives you A. Sorry, it gives you this element. Its power must belong to this field because so the action of the Galois group of sigma on this element, under action of sigma, this element gets multiplied by a root of 1 of this order. So that means that if I take the appropriate power of this element, I get an element invariant under sigma. So, okay, so all I need to show, so therefore, by Kummer, K tame is obtained from unramified extension by adding a single root for some A in K phi. So it remains to show that I can choose A with this property. And in order to do this, let's look at our homomorphism phi, which is a homomorphism, which is an isomorphism between this group and the group of roots of unity in K M B over K. So we have this homomorphism. This is phi. And on the other hand, so this is the Galois group of this extension of this extension. So if the extension has this form, then so you can construct another homomorphism to roots of unity, and this time in just in K unramified. So how it's produced? Well, you take a sigma here, and you send it to sigma of A to power 1 over E over A, 1 over E. Okay? So this element is equal to itself times a root of unity. So if I divide, I get a root of unity. And it's a homomorphism because, well, this is a straightforward computation using the fact that this field already contains all roots of unity. They're invariant in that action. So you may ask whether this, so this is also an isomorphism. So you have, and also you have projection here, right? The all roots of unity are integral, so you can reduce it modulo maximal ideal, so you get an isomorphism here. Почему? Ну, то, что фи-изоморфизм, это мы как-то доказали. Например, P — это просто ядро, а еще мы доказали суррективность. А это, ну, почему это изоморфизм? Ну, если если этот элемент инвариантен относительно какой-то степени сигма, то это означает, что эта степень сигма просто равняется единице в группе, потому что это образующий. Вот этот элемент, он является образующий вот этого поля. Значит, если он инвариантен относительно какого-то элемента из группы Гalois, Да, мы доказали инъективность, а размер у них одинаковый. Вот. Very good. So, so this diagram need not be commutative, but it's well. So why should it be commutative? It depends on A. So that means that, well, there exists an isomorphism here, right? These are abstractly isomorphic groups. Moreover, there is a projection, canonical identification between these two groups, given by the projection. However, if you want this diagram to be commutative, you have to modify this. You have to take, like, consider a homomorphism that takes epsilon to some, this is a cyclic group. What is an automorphism of a cyclic group? It's raising to some power relative prime to E prime. So it takes it to some epsilon to the R, where R is a given number relatively prime to E prime. Okay. But now I claim that what does it mean? It means that so what does it mean that this diagram, so if I consider this homomorphisms here, the diagram is going to be commutative, and what does it say about the evaluation of A?
R up to E prime.
So valuation of A is equal to R modulo E prime. Great. Right? So just because this phi is given by the same formula, except that you take this ratio and then you reduce it modulo the maximal ideal. But it's an isomorphism in roots of unity. So it's given by the same formula where you take for A generator, an element in uniformizer. You take an element of valuation 1. This phi is given by the same formula where for A is taken uniformizer. So if you have commutativity of this diagram, it implies this property. Okay, so but R is invertible modulo E prime. So replacing A by okay, maybe I will I would like to say R inverse mod E prime. Really. Okay. So I can modify my A. Ну, я хочу вот это А возвести в некоторую степень. Ну, я возвожу, значит, я знаю, что норма А, что валюация А, она взаимно проста с вот этим числом И прайм. Значит, я могу возвести в такую степень, чтобы норма А равнялась единице по модулю И прайм. Вот. Ну, а дальше я могу, безусловно, поделить на вот такую степень униформизующей, чтобы она в точности равнялась единице. Почему я могу поделить на такую степень? Ну, если я умножу на любую, или поделю на любую степень, вот такую, то, конечно, расширение не поменяется. Very good. So we have quite explicit description, and so let's, I want to finish this example by describing the Galois group of algebraic closure of K. So we have K, and we have K bar. Again, the same setup. So K is the fraction field of a complete discrete valuation domain with perfect residue field. So this is an infinite extension. And we have intermediate extension. We have, for example, unramified extensions. The composite of unramified extension is also unramified. So you have maximal unramified extension sitting here. And also, you have maximal tame extension sitting here. So I'm going to rephrase what we did here for finite extensions to the case of infinite extensions. And that's kind of almost automatic. Да. Да, он не зависит от выбора образующей. Значит, вот это отображение, вот оно как строится. Это просто действие на касательном пространстве. Нет, еще раз, здесь, значит, с идейной точки зрения происходит следующее. Я хотел бы вот сейчас перейти к бесконечному расширению. И здесь у меня есть некоторые проблемы. Если я буквально вот это вот буду пытаться там брать целое замыкание здесь, то например, ну, я никакого такого гомоморфизма φ не определю. Потому что, например, m будет равно m в квадрате. Любой элемент является квадратом в алгебраическом замыкании. Вот. Поэтому, значит, вот эти гомоморфизмы, как я их определил здесь, они нехорошо себя ведут при расширении полей. Да? Потому что если я возьму разветвленное расширение, то m фактор p в квадрате как-то поменяется. Я для того, чтобы с этим побороться, я хочу неразветвленный воспользоваться описанием слабо разветвленных расширений. Tame это означает, по-русски, значит, это будет ручное ветвление, которое такое вот очень явное. Я добавляю корни из элементов, у которых валюация равняется единице, и корни степени взаимно простой с характеристикой поля. Например, в случае ZP я добавляю корни из P, степени взаимно простой с характеристикой поля. Вот. Значит, вместо того, чтобы использовать вот эти вот φ, я буду использовать явное описание вот этого поля. Это композит конечных неразветвленных расширений. А конечные мы уже описали. Okay, so what can we say here? So the Galois group of K unramified over K, well, all we can say here is that it's Galois group of the residue field k bar over k. And another, so this group is, as we know, it's the same as the pi1 of spec A. So if you have a complete discrete valuation domain, then pi1 of this scheme is the same thing as pi1 of the closed point. This is an easier. Да. 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 Ну, как? Нет, ну что, ну для конечного расширения, я не знаю, что сказать. Ну, я могу, если я умножу, значит, какой у меня произвол здесь? Я могу взять А и умножить на какой-то элемент с нормой 0, то есть единицу. Ну, если эта единица сама является вот такой степенью, то ничего не поменяется. А если не является, то поменяется. Но если у меня есть любая единица в таком поле, то расширение, которое получается присоединением корня вот этой степени, оно не разветвлено. Поэтому если я вот в этой картинке, когда я рассматриваю максимальное неразделенное расширение, значит, вот если я возьму любой элемент, любые два элемента с нормой 1, то вот такие расширения будут одинаковы. Потому что они получаются одно из другого. Получается, ну, потому что корень из единицы любого обратимого элемента в кольце целых, он уже лежит в максимальном неразделенном расширении. Хорошо? Okay. So, yeah, and this, so this is this maps to pi1 spec k. This map is induced by embedding of spec k into spec k. This is a Gola group of k bar over k. This is a quotient. We have commutative diagram. So unramified extensions are in one-to-one correspondence with finite étale extensions of A. So, and tame, K tame, as we learned here, obtained from K unramified by adjoining roots of, well, I will say union of roots of uniformizer, where the union is taken over all E relatively prime to characteristic of the residue. Okay? So this is in K bar. So this is a very simple extension. And the Gola group of this extension, K tame over K, non-ramified, can be computed by Kummer theory using this homomorphism. So you can compute first Gola group of these extensions, finite extensions. These are cyclic groups of order E, canonically identified with roots of unity. And when you take the infinite extension, is going to be the limit over all E, again, relatively prime to characteristic, of roots of unity in K non-ramified. And non-canonically, this is isomorphic to the product over all L not equal to characteristic prime L of the residue field of ZL, right? So of all Tate modules, right? We don't have, well, E is relatively prime to P, so we only, so you can kind of write this, use Chinese remainder theorem to derive this decomposition.
Could it be ZL star?
No. So what is, so let's consider, so first let's write mu E as a product of all primary groups, right? So what if E is a power of L? Then the group of roots of unity is non-canonically isomorphic to Z mod L to the NZ. So you take the inverse limit of those groups. Why do you get star here?
Oh, I guess I get confused with cyclotomic.
Yeah, yes. It's not cyclotomic. It's different. So, good. So we have the following short exact sequence. We have the Galois group of these unramified extensions, this group. Then we have Galois group of K tame over K. And here we have the Galois group that we just compute. So this is the inertia group. Well, I won't use inertia anymore. So this is Galois group of K tame over K, non-ramified. So we have short exact sequence of groups. These two groups are abelian, but the extension need not be abelian. But you can compute explicitly what this extension is. So I claim that, well, first of all, so you have K, you have K tame. This extension comes from a sequence of normal extensions. So this is a normal. But there is also another intermediate extension, which is you just take K and adjoin, well, some roots of this polynomial. So union over all E of K of pi 1 over E. This is not a normal extension because I do not have, in general, roots of unity sitting here. So it is relatively prime to characteristic. So this subfield here defines a sort of, it's a subgroup. By Galois theory, it defines a subgroup which is need not be normal, but it projects isomorphically. So it defines a section, right? Which identifies this Galois group. This identification is non-canonical because it depends on the choice of roots of uniformizer. But abstractly, it's isomorphic to K tame, well, this Galois group is abstractly isomorphic to semi-direct product of the Galois group K bar over K and this group, which is normal subgroup. And I will put L not equal to characteristic of K ZL. So to complete the description of this group, I need to tell you how this group acts here. And you may guess what the answer is. This ZL are canonically obtained from this formula. And you have action of the Galois group of this field on the roots of unity. So it suggests that, well, so therefore, it suggests the following answer, where ZL of 1 is defined as a limit over powers of L, of roots of unity. And one can verify easily that that's indeed the action of this group here. So this describes this group explicitly. And, well, again, it's not quite canonical. What is canonical, however, is this short exact sequence and the action of this group by inner automorphisms on here is given by, well, so if you identify this group with roots of unity, then the action of this Galois group here is the natural one, given by its action roots of unity. So, and the last assertion is that the kernel of the homomorphism from Galois group of K bar over K to Galois group of K tame over K is a P group. And 0 in characteristic 0. Good. Well, so now let's return to our goal, and let's prove the main specialization theorem. We already have all the tools for doing this. And the tools that we are going to use is Zariski-Nagata purity and the ramification theory we just developed. Okay, so here is the what we'll do. So back to specialization. Theorem. So here is the setup, right? We have X over spec A, which is smooth, proper, a complete DVR, X0, which is a special fiber, is connected, and K is algebraically closed, the residue field of this discrete evaluation domain. And then, so we have the specialization map is a map from X K bar. K is a fraction field of A. First, you go to pi1 of xk.
That's not
Oh, yes, thank you, thank you. Okay. So pi1 of x, and then here by functoriality you have map from pi1 of x0, and the composition is called the specialization homomorphism. And the theorem is specialization is surjective and isomorphism on prime to characteristic of the residue field quotients. That is, if you have a finite group whose order is relatively prime to characteristic of the residue field, and any homomorphism, then it factors, well, uniquely through this group. Right, so, oh yes, specialization map, to define it, you have to use a theorem that we already proved, that this map is an isomorphism, right? That's also a non-trivial result, but we already know this. So again, an example to have in mind where how we are going to use this theorem. We are going to, for example, you can take for A, the ring of maximal unramified, for K, maximal unramified extension of ZP, or something like Witt vectors of algebraic closure. This is your A. You can take a curve, smooth projective curve over this base. So then x0 is a curve over incharacteristic P, and x capital K bar is a curve over an algebraically closed field of characteristic 0. So we know by comparison with complex fundamental, topological fundamental group, that this is the profinite completion of the usual topological fundamental group of a curve over C. And from this, we get information, some information about fundamental group of a smooth projective curve over FP bar. That's kind of why it's important. Okay, so what is the strategy here? So we already proved surjectivity, so we only want to prove this assertion, that any map from homomorphism from pi1 to G, where G is, order of G is relatively prime to characteristic of K, factors through pi1 of x0. So later in this course, we'll study kind of key results in Tal homology theory, which is called proper base change theorem and smooth base change theorem. So, so proper base change theorem is an analog of this statement. And smooth base change theorem is an analog of this statement that we are proving now. And in the case of so this is not kind of, well, this formally implies the smooth and proper base change theorems for H1, for first homology group, because H1 is just homomorphism from pi1 to ring of coefficients. And the relation in general is like this. Okay. So what we need to prove? So we need the following. So the explicitly, this assertion is reduced to the following. So for a Galois cover, yk of xk with Galois group of order prime to coprime to characteristic of k, we need to prove that there exists a finite extension. Well, a finite extension k of L such that the base change YL XL extends to a finite Galois, finite étale cover, YB over XB. Okay? That's our goal. So, that's equivalent to this statement. Well, strictly speaking, it's equivalent. Well, you need to know this not only for, I'm aware of myself, I do not want to fix, I want to kind of prove it for, not for single A, but for all also finite extensions of K, right? And then it's equivalent, becomes equivalent. Because the cover that I start with here is defined only over K bar. But therefore, it's defined over some finite extension. So by making base change first, you can reduce to this. Okay. So, okay, so I have 1 minute, so I will explain kind of our strategy. Then we'll, there will be some computations. We'll complete it next Wednesday. So the strategy will be the following. So we take normalization. Of this guy, of this guy, yx. So if this is étale, we win. If it's not étale, no, well, you have,
What is D?
oh, it's, yeah, so I take, okay, so I have in normalization of x in fraction field of yk. No L. L is k. So if already for L equal to k, this happens to be étale, we win. So if not, there is some open subset, for example, x capital K, over which this map is étale. And they can take the largest open subset with this property. So this is locus where this normalization F is étal. Now, by purity, by Zariski-Nagata purity, I know that if U contains all points of codimension 1, then U is everything. Because the ramification locus, the complement to U, is pure of codimension 2 or higher. Of codimension 1, sorry. If U is the complement to U has codimension at least 2, then U must be everything. So the only problems is, that means that U must contain some points of codimension 1. And I'm going to localize this picture in points of codimension 1. So what are the points of codimension 1 in U where this map is not étal? There is only one point, namely the generic point of x0. So if F is not étal, then what we have is the following. So we can look at generic point of x0. So look at the generic point eta of x0. This is the only point of codimension 1 that is in the complement, right? Because what are other points of codimension 1? Other points of codimension 1 are in the generic fiber, are already in xk. So you have the following picture. This is spec k. This is spec a. So this is special point. This is your x0, and this is xk. So and I have U here. So I want to show that U is everything. So it's enough to show that U contains all points of codimension 1. And what are points of codimension 1? These are some divisors like this that project dominantly here, but then the generic point is already in xk. And the only bad divisor is this divisor. So I have one discrete valuation domain, and I have integral closure of this guy in fraction field of y. So here we have an extension of a discrete valuation domain. And if I know that this is unramified, then we win. Is ramified. So in order to check that this is ramified, well, unramified, it suffices to check that the extension of the residue field is separable. And we will control it using the fact that G has order relative prime to P. And then we have to prove that the index, the ramification index, is equal to 1. So it need not be 1, but after replacing K by some finite extension, so the ramification index of this guy is equal to some number, E. It turns out that if you take for L the extension obtained by extracting eth root of the uniformizer, then it works. So we will check by explicit computation, then the normalization is indeed étal. So you look at the ramification index of this extension, call it E, and then take, so this is E, and then take for L, K adjoining pi 1 over E. And it kills ramification. This trick is called a Bianchi's lemma. Okay, so I'll have to stop here. Ну, там много разных. Мне важно знать, что И взаимно просто с P. Откуда можно заключить, что И взаимно просто с P? Что индекс светления взаимно просто с P? Но вообще говоря, если у меня есть какое-то расширение, у которого даже степень взаимно проста с P, сказать, какие там индексы ветвления невозможно. Но если у меня расширение ГУА, то я знаю, что индекс ветвления делит порядок группы.
Чтобы они одинаковые.